here I brought it's a cross section of this transportation flow line, okay, pipeline. There is a company. If you know during summer they have some nice beaches, not like in the Caribbean, but you know for Norwegian standards they are quite okay. There is a company in Erkanget that they produce these pipes, okay, and they roll them in boats and then they deliver them to the fields. So if you know for some time to organize a visit, maybe a bit too late, but if you are in the area and you can just you know have a tour, they have some very nice things that you can see from the road. Okay, so here you have kind of the inner wall of the pipe. Okay, then you have all the insulation layers, and that's just a protective layer. Okay, so just pass it around. So today the plan is we will continue with temperature. Some like you know just to continue the discussion we had last class, and then I will talk a bit about processing. There is a full course about processing that some of you are supposed to take in the third, some of you in the fourth year. But just to highlight some things that are important for operations, for field design. And yeah, and that's the plan. Usually Thursday I have a very big plan, and you know it's not. I don't have too much time. So the other thing is that the results of exercise 2, I have them almost finished, but I need like 3 hours to sit and do some final correction. But I haven't had time this week. So probably will be for tomorrow, if not for early next week, I hope. Okay, but they're already in the pipeline and I hope to have it published soon. Now the fourth set is already published, so it has 2 problems. And the first one is we are studying the Hans satellite of Ivar that just came into production last November, I think, October. And to make first pressure drop and temperature drop calculations in the main pipe, and then to see if you fall just below the cloud point in the wax appearance temperature. And for that I did an example in class with a well, and you will have just to use the same procedure for a pipe. I'm giving the composition, the mass flow rate, I think, yeah, just oil and gas, and I'm giving a temperature, an expression for temperature that I told you last class I will derive it, try to derive partly here today. Okay, so you see where it comes from. Then so that's relatively simple, and then the other example is to study again temperature and pressure drop, but in the main transportation line from the Snøhvit, Snow White field, Blancanieves in Spanish, to shore, 146 kilometers, and for that you will use the software HYSYS. Okay, some of you have experience using HYSYS before. How many of you? Maybe 10? No, nobody. Okay, 1, 2, only 2, 3, 4, 5. You are shy. Just they will come up more and more. If I say who, the one that has seen HYSYS gets a prize, all of them will lift their hands up. Yeah. So really, it's so I will try next week to make an exercise, but related to processing in class using HYSYS. But really, it's a very friendly program. It's really easy to learn. So I suggest if you want to start working right away on the exercise, to here at the end you have HYSYS. You can run it remotely. It runs on a server, and then you just have a window that shows you the interface, so you don't have to install it on your computer. Alternatively, if you want to use it on a computer, it's installed on the 3rd floor, some computers. And I recommend, that's kind of a very basic example of expansion of fluid in a valve, but I suggest also, last year we discussed that exercise in class, so you can go directly at 1 hour and 7 minutes in that video, and also from the beginning on that video. Okay, then you learn how to use the tool and also apply it exactly to that problem. Okay? So it's not so difficult. If you find some major problems, some things that you don't understand, we can take some clarification sessions. You can ask also the assistants. They had the exercise last year. Okay. So the main point is to simulate the pipeline, okay, not the rest of the system. So let me change just that part, okay? And we are going to make a simplification on the profile. Just make a horizontal pipe and then going up. Well, in reality, it has some valleys up and down, someplace here, but we just simplified, you know, to make it a bit easier for you. Yep. Then one of the things is that we talked we talked on Tuesday about what the expansion in a choke does to temperature. You see that the reduction in temperature is very dramatic. So I want you to add, because we know that the temperature of the wells is very similar to reservoir temperature, like 90 degrees. But then you have a very strong expansion that you calculated. Okay, you did it for Tanzania block 2, but for Znovi it is also very high. It's 162 bar. So I say, using that pressure drop, take it to the, so that will be the temperature that you have at the template, and then you just assume that the temperature remains more or less the same until the PLEM. And then you perform your pressure and temperature calculations. You don't have to do it, okay? You just use HYSYS to do it. And you find out how is the pressure and temperature profile, and if you go inside the hydrate region, and the hydrate region is the line that is given here, okay? Temperature and pressure. So you have to make exactly like what I have painted in class. You have to make first the phase envelope, okay? So you have to take the collection of points and put them in Excel. Then you have to take pressure and temperature, how they progress from point 1, because that will be the PLEM, until point 2, that will be shore. And then the hydrate line, you also have it, and then you see if that happens or this happens or what happens, okay? And I think that's the main but the main task really is to learn to use the tool and to know how to extract the information from it. So I suggest just go ahead and watch those videos, try to learn it by yourselves, and next week probably I will try to have one class example, but about something else, about processing. Okay? Any questions so far about the set? It's for, I put the deadline for Sunday before, before Easter, because I imagine that you want to spend your, if you are going to take a break or something, you don't want to have this exercise hanging on your head, I think. But, if we need some more time, we can stretch it, but I really prefer that you finish before. Okay, so let's continue with what we were doing last time. And I'm going to make the deduction of this heat transfer coefficient, and I will use it only for 3 layers, what we have in the exercise 1. So let's say we have first the pipe, then we have the pipe wall, okay, that will be up to that point, this silver area here, and I will call that R1, R2, and then to make things a bit simpler, you have here more layers than that, but I will just say that you have just insulation, so the R3, and then just outside you have the C, okay, that's the seabed, and that the pipe is exposed to the seabed, so here you have T ambient, and here you have T fluid. So what you have is what we mentioned last time. First, going from in and out, we have convection, and actually it's called forced convection on internal flow. and let's maybe call that, we can call that T1, that temperature T2, and that temperature T3. Okay. So and we can represent that by 2 pi r1 times a distance. Okay, that the distance if we see the pipe from outside. And H internal times T fluid minus T1. Okay? Now, one thing that I want to call to your attention is that here, that H really might be, you know, if you want to really be kind of formal about it, if you see what's happening inside the pipe. Okay, if you have a mixed flow, then you might say, okay, it's very uniform, so I can assume that there is an average H that dissipates the heat inside. Okay, but if I have, for example, slug flow, okay, or I have annular flow, or I have any other kind of flow, okay, in that case I will have some patches that have some H, and there will have some patches that have another H. Okay, and then the thing becomes very complex. So in this course, we're going to keep it simple. We're going to say we have an H that God gave it to us. Some expert gave it to us. But just be aware that the thing can be very, very complex depending on the flow pattern, and you can make it it can be much more complicated. But in this case, we're going to make it simple. So then you have conduction in the pipe wall, and there we have Q 2 pi L again K of the pipe, and here you have T1 minus T2 over ln of R2 over R1. Okay. Then you have again conduction in insulating layer, and again is Q equal 2 pi L, and then here K, the conductivity has to be of the insulation times T2 minus T3 over ln of R3 over R2. Someone has to be doing quality control, making sure that I don't mess up. Otherwise, if it's at the beginning, then we will have to go back. If you do it late, you notice late, then we have to go back many pages. So then the last part is its convection in the sea. Okay, and here I want also to call, because you have two types of convection. One of them that is forced, that you have like the fluid is in movement against the surface, okay, and is forced convection. And you have another type which is that the fluid is not moving, is stagnating, but due to the heating of the fluid, because you have, for example, in the case of the water, you have here some particles that are close to the wall, so they are going to become hot, their density is going to reduce, and then they're going to go up, and then the heavy molecules are going to go down in contact. So you have some kind of circulation, but it's something that is a product of the heat, okay, of the heat transfer. So that's what we call kind of a free convection, okay, free convection. And truly in the ocean you have two things, because you have that phenomena and you have also some currents that might be flowing over the pipe. So that H is really a mixture of those things, but again, to keep it simple, we're going just to say that 2 pi R, and in that case it's R3, times H, that we can call H out, L, okay, and T3 minus T ambient, and that's all. Okay. So now the next step, I'm going to, for each one of these equations, I'm going to clear the pressure difference, and I'm going to sum all of them up. Okay, Q, I can take it as a common factor for all of them. So at the end, what I will end up is, so the first one will be 1 over 2 pi r1 L, okay, plus ln of r2 over r1 2 pi r, sorry, okay, yeah, I just made kind of a shortcut, but the only thing is I clear that difference, so that gives you the heat divided by that, okay, and then I sum all of them up, and you see that you have a common factor called Q, the heat that is transferred. And let's see if I didn't make any mistake. H out, then you have ln 3 over 2. Yeah, looks okay. So then you see that all of them, you have all of these factors that they have different signs. So all of them are cancelled, and at the end you get T of the fluid minus T ambient. Okay, that is the main temperature gradient. And remember, I told you it's like difference in voltage. What is driving in case of, well, like if we make the analogy to flowing pipes, is the difference in pressure, in energy, what is driving the flow. That is equal to Q, and here I say I want to make the same trick. I want to say, to make it similar to an equation, I want to make it similar to something like, I have a heat transfer coefficient called U, that is overall heat transfer coefficient, times an area, and that area is, say, 2 pi r, that is the perimeter, times L. Okay, and then comes two things. I have to decide first which area I'm going to use as a reference. Is it going to be the inner area? Is it going to be this perimeter? Or is it going to be the outer perimeter? Okay, so what is typical and what HYSYS, for example, has is to use the outer. So in this case I use R3L, okay? And I can clear, if I make that expression equal to that, okay? Let me just move it to the left. Sorry. Okay. Then you will see, you can take, sorry, the area should be down, okay? Because we want to make it, sorry, that was a mistake. Just like with convection, okay, that you have Q equal to an area times a coefficient times a delta T. Okay, we want to look like that, so then delta T equal Q over A times H. Okay, so that here should be 1 over U times 2 pi R 3 times L. Okay, and from there we can clear exactly what will be the value of U. Let's make another page. So 1 over U will be okay, remember I have to so if you see here I have R3 and here I don't have any R3, so I have to put it inside, so that will be let's see, H in R1 over R3 plus ln R2 over R1 and the only one that I really am clearing, taking out the three factors, is the outer, the heat, the convection in the outer layer. Okay, so let's see. Just do some quality control. Yep, looks okay. And that's the expression that you have to use for in the exercise to calculate the overall heat transfer coefficient. And you can make it really, if you have multiple layers, if you have, for example, soil, if you have, because you might have, that's kind of a plastic, okay, a polymer. Sometimes you might have concrete. You have to change the properties. Sometimes it might be buried in gravel, so you have to use the conductivity of the gravel. Also, I told you that you can use the same idea for wells, okay, that you have in the wells. You have an annular space with mud, and then you have cement casing, you have many multiple layers. You can do the same approach. The only thing is that that expression will be bigger and bigger and bigger, but it's very, very practical. I think it's very powerful, you know, for heat transfer. All the time you can find an equivalent overall heat transfer coefficient. Okay, that's overall heat transfer coefficient. Okay, and that in that case is referred to outer area. Okay, remember, you all the time have to ask, usually is the outer area, but sometimes might be something different. Also, something to call to your attention is that when we have a flowing well, for example, that was shut in, initially had no production. So in that case, the temperature profile is just the opposite. The geothermal temperature profile, right? From T reservoir all the way to T of the sea. And that's, we call the reservoir, and that will be the wellhead. But after I start flowing, then the fluid that is inside, the fluid that is flowing inside starts to heat the formation at that particular depth. Okay, starts sending heat to the formation, and the formation will become warmer and warmer and warmer. Okay, and initially, so we'll have, if we try to paint how it will look like, it will be, that will be at time 0. Then, for example, time 1, then time 2, okay? But it won't heat exactly at the temperature of the fluid. It won't reach never that temperature, okay? It will reach something in between, the original geothermal gradient and the temperature of the fluid, that of course is not constant, but also will have, so that will be the temperature of the fluid, and that's the temperature of the formation far away from the well, and kind of the near wellbore will kind of be, you know, heated by the flow in the well. So sometimes for some well models you see that they have an option to see how many days into production you want to calculate. Okay, they say they apply a very similar equation, but then they say, for which day do you want to calculate? 1 day, 20 days of production, 100 days of production. Maybe that, for some wells, that might take a long time, maybe 3 months, okay, to warm up all the area around the wellbore. So in that case, we're not going to make it here in class, but just to make you aware of that, what is done usually is that you have, is like T ambient is located at a certain radius, okay? And that radius is a function of time. So I apply exactly the same equation, but the only thing is that the radius will change with time. First will be very small, and then will become bigger and bigger and bigger and bigger, where I have like my ambient temperature. And in reality, it's not exactly, you know, you shouldn't, not say you shouldn't do it, but is an approximation, because really it's like a transient phenomena. Okay, you have kind of a warming up phenomena. So you should solve it with a completely kind of transient model, a model that where you don't make this assumption. Okay, when you want to calculate the variation with time. Okay, but has an approximation, and this is something that people have done in the 50s. They didn't have Excel, they didn't have MATLAB, they didn't have computers, so they found a very clever way to solve the equations, but to say I have now an R, the T ambient will be located at a position R that varies with time. Okay, a very clever way. A guy in Stanford called Ramey, that he did it for water injection wells from Stanford, and I think the date was maybe the 1956. That was his paper. Well, he later went to Stanford, but I think that was when he was working for Moby. And the idea is that that R, where the ambient with time, okay, initially is just very close, and then it starts getting away, 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 until you reach, until you warm up exactly. That's the area where you warm up, that you are warming up. Okay, that is heating. Okay, just to make you aware of that. So sometimes we have that the simulator is asking for which time do you want it. Okay, and for us, really, if we're going to make studies in the life, you assume that really it always reaches that it reaches very quickly. But if you're doing, for example, well testing analysis, it might be relevant to know exactly in which day of production you are. Okay? So now that we have that heat transfer coefficient, we go back to our equation that we had from last, to the energy equation in the fluid. Okay, that was dq, if you remember, that was from the first law in open systems, del equal to mass flow, and then you had some things. Okay. And that's, I think, was a question that if this was the, what angle was it? Okay, and that C, it stands for elevation between 2 points. You have 1.2 and 1. So that's C is elevation, and L is the distance between those points. So, and if you say that that's the angle, so set over L equal to sine of theta. So it should be the angle from the horizontal. So that's sine of theta g okay. So now let's make some, to make that equation, to put it in the kind of in the form that in the shape that we are going to use it. We're going to assume that we are talking about neglecting velocity changes along the pipe. Okay, so that is valid maybe if you have kind of a heavy oil, okay, or with plus water, that you had no gas liberation. So then that term can go away. And also, if you remember your thermodynamics, dH, if it's a liquid, dH is Cp, that is a function of temperature, over dt, right? The specific heat at constant pressure. And then for gas, you know that that dH is equal to Cp dt plus something called Joule-Thomson coefficient. times dP. Okay, so that's exactly in a choke. In that case that we were analyzing on Tuesday, that term is exactly what gives us the cooling. Okay, the cooling effect. If there is a change in pressure, this Joule-Thomson coefficient causes a change in enthalpy, thus the fluid has to change in temperature. Okay, but we are going to neglect it for now. Just just a disclaimer. The enthalpy, okay, is a thermodynamic property that depends on pressure and temperature. That means if you have a EOS model, for example, or if you have a correlation, or if you have something, you can just use it straight away. Okay? If you have, for example, your program, your own HYSYS, you want to use HYSYS to calculate that, that's perfectly okay. But if not, those are some of the two approaches that we use. Okay, for gas or compressible fluid, or for liquid we just used, and actually I'm not sure if you remember in Prosper when we had our session in the lab, there was an option that said rough temperature approximation, very accurate temperature approximation. Do you remember that or not? Let me see if I can open it. Okay, the first you say pressure and temperature. Okay, model rough approximation, and that it's assuming that everything behaves has like an average CP. Okay, it's neglecting this Joule-Thomson coefficient, and it's just assuming that you have a CP that is average. It behaves almost like a liquid. Enthalpy balance is using that method, assuming the Joule-Thomson coefficient, and I'm not sure what is improved approximation, but okay, so you can specify, because it really saves some time to neglect that term. Okay, to try to compute that term is kind of a bit cumbersome. Okay, so I neglect all of that. I substitute the rest in that equation. So I have dq dl equal to mass flow of cp dt dl plus sine of theta g. Okay, and then I have to plug in the heat. If you remember, the heat was just 2 pi r out times this u, okay, out, times Tf minus T ambient. Okay, but we're going to plug it in this equation. Remember that the first law it has a convention. Okay, when we had the first law that you had coming in 1, coming out 2, and you had this control volume, the convention was that if Q is going out, it's negative, okay, right? When Q is coming in, it's positive, and when work or power is coming out, it's positive, and when it's coming in, it's negative, right? Remember that back from kindergarten or from your studies when they were teaching it. So in that case we have to change the sign, okay, because that gives us that heat is coming out of the system, and here it gives a positive number, so we have to put a minus in front. So let's plug it in. The derivative, we have to take dl out, so it will be 2 pi r out u out T of the fluid minus T of the ambient equal to m Cp dt dl plus mg sine of theta. Okay, and I think I forgot to put the minus, right? Here should be a minus because it's coming outside of the control volume. And now I will stop boring you with all the, so I'll just you have to solve that differential equation, and you can use this integrand method, that you use this exponent, that because at the end that's an equation that is dx plus a times y equals c, and those equations you can solve it with this old method that you saw not in Barnehage but even before, but I don't want to bore you with that, so let's just take the screenshot. Okay, and that's how you get the expression that is in the exercise. Okay, I'm assuming that it behaves like a liquid, and x is measured from this TO is the temperature at the beginning of the section. TO is here at x equals 0, and with this one I can predict how the temperature will change along the pipe. Okay. Now some of you ask, what happens if then let's say the inclination change. Now I'm looking at different sections of pipe going up and down, up and down. So then I have to apply the equation, one equation for that segment, then I find the T inlet of the next segment, then I have to calculate U, or in my case A, okay, I call it A, okay, A is MCP over 2 pi R out times U. So I have to calculate, be careful that I can use that equation only if that doesn't change, and also that doesn't change. If I have, for example, commingling of 3 wells, I have to apply one equation down to here, one equation down to here, then I have to make a mixing, that if you remember, the equation is just, I have just 3 things that come in and 1 that comes out, M1 H1 plus M2 H2 equal M3, and then I progress again on that section. That actually is something that the software has to do when you have a mixing point. You have to calculate the temperature at the outlet. With this expression you calculate the enthalpy, and you have pressure, so you can calculate temperature. But we are not going to see that. So in your exercise you have only 2 segments, and CP, I'm telling you, you assume constant, so really you have to make one equation from here to here and one equation from here to here. Okay, so the only thing that changes is this the sign of that. Okay, then we are done with this temperature equation. Any question? No? Let's take a break, 15 minutes, and let's start with the processing part. So let's talk a bit about now that part is we were having now some discussion in the break that actually the temperature what these guys are obtaining is that the temperature you have 85, and at the end base of the riser you have 11, and then when you go up actually starts to warm up and it has 12. So they suspect that there is a sign in the equation that is wrong, okay, that you should have minus, you should use instead of sine G, you should use minus G. But I'm not so sure, so they will give us an update once they find out. They take the responsibility, they are the consultant to the professor in class. So it's good to have consultants, but don't have money, so I cannot pay you. So, but it's a good practice for the future. So today you will probably, if you find something, communicate on the forum. Yeah. So let's talk about processing. And processing of hydrocarbon fluids, and we're going to limit our discussion to equipment on the platform. What do we usually have on the platform? because processing is a relatively very big term that involves also some things that you have onshore, refineries, some other processes that we, in the platform we typically don't have space to squeeze all of that. So we have just the minimum that we need. And basically I have the reservoir, some fluids coming from the reservoir. Okay, that typically are oil, gas, water, plus some ugly things we don't want, asphaltenes or sand or etc. So we have first one stage that is, and is the most important, that is separation and stabilization. Where we are going to get three streams, and here I think I have mentioned that convention before, but I want you to memorize it. Oil, green, gas, red, and blue, water. Okay, memorize it. If you want to practice to your friend in Muhol, you wake him up 2 a.m. in the morning, middle of the night, what color is oil? And if he doesn't answer, until he remembers, okay? Just say it by heart. Green, green, gas. Okay. So we have for the water, okay, we have de-oiling, basically, and degassing. And we have the water can go either for injection or can go just for disposal to sea. Oil, usually we have dehydration, and we have desalting, and that oil usually goes to the tanker. We don't have really in the North Sea, we don't have oil pipelines. Some other places we can just hook it up to the pipeline. And gas, we have dehydration, okay, contaminant removal, okay, that we say this can be H2S typically, or it can be also mercury. Dehydration, contaminant removal, yeah, and that's all. And this gas usually goes to a pipeline. And the pipeline can take it to either to the European distribution system, that goes via UK, or you can also go like in Snøhvit, that you go to a LNG plant further, okay? But usually to the gas distribution network. Or LNG plant. But now the only case we have in Norway, it's Hammerfest. The plant is in Hammerfest in Melkøya. Okay, but before that we forgot something else. To transport it, usually remember that we are at a low pressure. Remember, the separator is like the, when we say it's like our anchor, okay, of the whole production system, the upstream production system. I know that the pressure will remain constant no matter what. So that pressure is usually low, okay, we will see right away, but it's usually low, such that I cannot just plug in the pipe to the line and it will be transported. I have to compress it first. So here I have compression. And here between that, I also, before injection, I might have also to have to do pumping. Okay, so now I'm going to make it first very simple. Okay, and we are going to look first into that box. Okay, what we have that will make separation. And it's very simple. I just have a series of separation stages with gravity vessels. So let's use the convention. Okay, I have a rate of oil coming out, and then I have gas, red, okay, and I have Q gas. Now let's that's the basis. Okay, I have just a gravity separator with all the liquids separate, and then I take from the upper part I take the gas, and from the lower part I take the liquid. Very simple. But now we see that we need some things to make it work. Okay, we cannot leave it like that. So the first thing is that they have different pressure. Okay, that one has pressure 1. Okay, pressure 1 is typically for oil fields. It's equal to around 50 bar. And for gas, it usually can be higher. Okay, for oil fields, 50 bar. For we don't call it heavy, but like low GOR oils, it can be lower. So let me make that comment just not here, but maybe here. It can be down to maybe 20, okay, 25 bar. And for gas, it is usually higher than 50. But we will see right away, we are going to see why is that. But just keep in mind that, so here I have 50, like 50 bar. That here will be very close to standard conditions. So that might be maybe 2 bar. And here you have something in between, okay? Might be pressure, let's put it here, 16 bar. And that pressure maybe 50 bar. Okay, just to put some numbers that, but the pressure is reducing. That will be the first separation stage, or the high pressure. They call it the first separation stage. Also called HP high pressure. That will be the medium second separation stage, or medium pressure MP, and the third separation stage, or low pressure. Usually we have in the North Sea, usually we use 3 stages. Okay, more or less typical three separation stages. So you see that first the fluid coming out, it comes at different pressure. Okay, so if you're going to merge them on the same line, you have to put something that bridges the pressure difference. Okay, between that line will be at 50 bar and that will be at 16. So if you just connect them, you will never get flow from that pipe into that one. Okay, you will get actually the opposite. So what you have to put is a compressor. Okay, what happens, can I make, just to put the compressor right away like that? Okay, Okay, compressor, remember I enter into the big side, the white side, and then I go out on the smaller side. Okay, indicating that initially I have a very high volume, and when I compress it, it occupies less volume. So I cannot do that exactly because remember, these machines, compressor, they are very delicate machines, so also very expensive, but they are very delicate. They can only work, so compressor can only work with gas, okay, with very dry gas. It doesn't accept at all any particle because the velocities are very high, and if you have any particle of liquid, it can start. It has like some let's see, some blades, okay, for the fluid goes on that direction on those blades, and if it has some droplets, the liquid will start to impinge on these blades, and it will cause erosion, and it will damage the compressor very quickly. So compressor really doesn't like at all any liquid. And if you see the problem, when you see exactly that fluid that we are extracting in every separation stage, okay, if you see the phase envelope PT, okay, let's say that you are someplace here, right? And then you separate. So what you're doing basically is that you are, so that will be separator fluid. Maybe I should put it black because that's not good. Black. Okay. So it will generate, we can think like it generates two fluids, okay? It's not exactly like that, but it's very close. So it has one fluid that is, so that will be separator oil, okay? Exactly what comes if I put my separator here. That will be 1, that will be 2, that will be 3. So that's 1, that will be 2, and 3 will be some gas where, okay, that's, so the point is that the fluid that leads into is at the bubble point, at the bubble point, okay, it's exactly there in that point in the curve, and the fluid that leaves here is in the dew point. Okay, so that indicates that any, and what will happen, you know, these are pipe segments, so what will happen through that is that the pressure and temperature will decrease, okay, and what that happens, that point tends to go inside, okay, the envelope, okay, it tends to have some condensation. And also the same thing with the oil, when the pressure and the temperature go down, also it tends to release some bubbles of gas. Okay, that clear? Yep. So then the solution is, before the compressor, then I know I have a very high risk of introducing some droplets of liquid to the compressor or some bubbles of gas to the pump, okay, that also the pump doesn't like at all any gas. So what we make is, I will make, first I will force it to release part of that liquid, so I will put a cooler. Then I have already in this stream, I think that I will have some liquid in that fluid, so then I will put a container called a scrubber. It's like a vertical separator, and then only then I take and I put it in the compressor. Okay, and this will have some liquid coming down that I usually, so maybe I should maybe put it differently. Okay, and then that liquid I just take it and I have to re-inject it here, and I usually also put a pump. Okay, because I will have some losses from here to here, then the pressure will be lower than the second stage separation pressure. Okay, so it's becoming messy, but I have to do the same thing for this one. Okay, exactly the same. So the trick is I lower the temperature, induce condensation, then I take out that liquid, and that liquid won't be anymore at the saturation point. Okay, won't be so close, and then I can just introduce it to the compressor. Yeah, so let's copy maybe that.
Sir?
Yes.
Why you don't have it on the first separator?
On the first separator, you also have it. You also have
Compressor?
well, we start, but remember here that pressure is 50. Okay. That pressure is 50, and we have to take it for transportation to a much higher pressure. So here at the end, there should be another compressor that increases it to the final transportation pressure of the line. And because of that, I have to do exactly the same here in the first stage. Okay? It's not exactly to commingle it with the others, but it's just to be able to send it to further to the downstream compressor. Okay, but you're going to get just now, after I finish that, just now a diagram of a real field. Okay, and I do the same. It's becoming a bit messy. Okay. Now, what do I do with the liquid? Okay, so remember here we had also some things that we forgot. We have some control valves that we have been speaking quite a lot about them. So we have to keep them here because they are the ones that make sure that our separator pressure remains constant. So also on the liquid line, exactly the same thing. Okay, you have a control valve. So just the flow, the losses from this point to that point will be enough to create some liberation of bubbles of gas in the liquid. So that's something we don't want and we want to avoid. So we use exactly the same trick. I put a cooler. Okay. And then also another trick that is used is that always I have to increase a bit the pressure at the suction increase a bit the pressure by putting them in a different height. Okay, so if I just put them, let's say 1 or 2 meters different in height, okay, then the pressure will increase. Okay, and then we'll be kind of going farther away from the. If the pressure increases a bit, I will be pulling it up farther away from the bubble point line. Okay, and here I'm missing the valve. So, sorry. Okay. So I'm going now to circulate. Okay, so here we have two here, and the rest you can just pass it along. Okay, so everyone has the drawing, yeah? So if you see here, you have the the production. Okay, and then for now neglect that test separator. Okay, we know that we want sometimes to have a test separator where we can send, if we have two flow lines, we can send one of the wells to that line and the other one to the main production line. But for now, just forget it. So we have first stage. Okay, we have the the gas coming out. We have the second stage and the third stage, and you see here the values 87. So Christine, that's gas, well, like gas condensate field. Okay, so that's why the pressure is slightly higher. You have first, second, and third stage, and you have that cooler in between the stages on the oil line, and then you see you go on the gas side. So follow just the gas on the first stage, for example, goes up. Okay, then you have that square that represents a cooler. Then you have a scrubber. Okay, and that will be kind of equivalent to that line. Okay, that line that goes to that line here. Okay, so let me just put that also. Good that I have space here. Okay, so you see that the same thing is happening for every stage. If we go now to the second stage, again I'm taking the gas out, I'm cooling it, I'm using a scrubber, I'm using the pump to send the liquid through the inlet of the second separator, and then I'm compressing it to take it to the same line. You know, in this case it goes, all of the streams go again through the scrubber of the first stage. Okay, and also for the second one exactly the same. And these things, intermediate things that we have, are just because of those fluids that come out of the separator, they are at saturation conditions. Okay, so and they have different pressures. So to merge all of them, I need first to increase the pressure. Okay, so I ask you now, why do we increase the pressure rather than take them down, all of them to the same pressure? Just to see if you're awake.
We needed to transport through pipeline where we need higher pressure.
Okay, in the pipeline to transport I need high pressure, so it really doesn't make sense to bring everything down to take it up again. I want just to keep up and then from there compress. Okay, that clear more or less? Yeah. Okay, so then I have the gas goes to, so the gas, where should the gas go? That's that part. Okay, it's separation and stabilization. I have the gas goes to dehydration, if any, removal of contaminant, and then compression. Okay, so if you see the drawing of Christine, you see that the gas, after that's the whole gas of the platform. Then it goes to dehydration using this tech glycol contactor. Glycol is it likes too much the water. Okay, so the water tends to jump out of the gas and goes to the glycol. Then you have mercury absorber. Okay, and then you have the main compressor. You have again a cooler, a scrubber, and then you have the main compressor that sends the gas for export. In that case, 210 bar and 50 Celsius. Okay. But remember also, we can use the gas can be used for gas lift. Okay, I can use it also for fuel for the gas turbines, that they give power for all equipment. And there's something else. gas for injection. Okay, gas for gas lift, also for gas injection. Okay, for pressure support in the reservoir. We can use it for fuel. Is there any other use of gas? Pipeline? I don't think so, no? You can also have it if you have this base injection, gas injection in the riser race. You can also have it for that purpose. Okay, but all of them have to go through that process, the hydration process. But also the important thing is that sometimes the gas that is reported, there is a meter in the export line, and that's what the company reports to the government. But all the other gas, the company measures how much, but it doesn't have to report it, how much gas it's using for injection or how much gas it's using for. So sometimes the values that you get for the field, they are the sales gas, but that's not exactly what you're producing. You might be producing a bit more. So just be aware of that. Okay? So now the oil, we don't do too much with the oil. In that case, we just have from every stage we take it to a meter, then we have a cooler and a pump that will send it to another Osgartzi, I think that's FPSO, I think, and further to the tanker. Okay? Now what happens with the gas, with the water? Okay, let me take that diagram. Okay, the water we use usually after I have, the water is usually separated, and it depends a bit where you do it, but most of it is separated on the first stage separation, separator. Okay, then you take it, and typically the concentration of that water coming out, is called oil in water concentration, is typically between 1000 ppm and 500 ppm. Okay? And the maximum that these are cyclones that they induce a very strong rotation on the fluid, and then due to the centrifugal force, the water goes on the outside and the oil stays in the center. Okay, so then you separate oil and water. Then all of that goes to a cooler again, to a kind of a big tank where you, if you have any gas dissolved in the water, it has some time to be released. Okay, and that can be taken further to the gas compression chain, and then you just dispose it to the sea. Okay, sometimes we can have also, to improve separation, we can have also what is called flotation unit, but it's also called induced gas flotation. Okay, or flotation units, they're also called. That they consist on injecting, we are not going to go in detail into them, but they consist in injecting gas in the oil and water mixture, and the gas causes that all the oil droplets, they start to kind of not grow, but they start to merge a bit with the gas droplets. Okay, and then this gas, they drag them further, and that allows to separate. But that also depends on the case. So basically, very simple, 3 stages or 2 stages. Then you have the hydrocyclones for water separation on the water side. Then you have some compressors, scrubbers, and coolers just to be able to merge all of them. And then you have the gassy hydration unit. Not much else, okay? That's more or less what we have in a, very roughly said, in a platform or in the fields in the North Sea. Yeah? That more or less clear? Now we go to the design. So let me see if I'm missing something. Okay. Let's talk a bit about typical capacities. Okay, so we have for oil, we have rates, processing rates between 8,000 standard cubic meter per day all the way to 50,000 cubic meter per day. Processing, that's processing facilities of an oil field, okay? Gas can be between 1.5 and 8.5 million standard cubic meter per day. And yeah, water, I think I don't have it. No, and what we discussed before, the pressure of the high pressure stage is around 50 bar. Okay. Number of stages, usually it's 3. Okay. A number of trains, it's 1 or 2. A train is that configuration. Okay, a train is the set of 3 separators. So sometimes if the volume are too high, I can have just a parallel train with the same capacity. Okay, so just some okay, somehow how, so let's see how processing facilities are or affect the field design process. Okay. So one of the most important things is the pressure of the first stage separator. Okay. And it has impact on different things, and let's go one by one. So first, a high pressure gives better recovery, better condensate recovery. Okay. If I put the first stage separator pressure very high, that will give me better recovery. That's why, or very simply said, okay, that's the exercise maybe we will do in class next week. So those components, C1 and C2, usually they tend to go to the gas, okay? No doubt. They are very clear, they are very, if we say Democrats, Republican, they say, well, I have no doubt I'm, Democrat or Republican. And then these guys from here, more or less from C5 down or C4 down, they tend very much to go to the oil, no matter at which pressure do you separate. But then you have some guys in between that they are the yes and no. Okay, they have, if you convince them, they can go here, or if you convince them otherwise, they can go there. And that, even if you don't believe it, it makes a very big difference at the end on the volumes that you have of gas and oil. Okay? And one way to convince them is to have that pressure, the pressure of the first stage, relatively high. Okay? So high pressure gives better condensate recovery, or better liquid, let's call it liquid recovery. Okay? But also, so what is the problem with high pressures? If you see it from the production side, from the available versus required. Okay? If you make the first stage separator high, then remember that what is driving the flow is the difference between reservoir pressure and separator pressure. If I increase this one, that means that I will have less flow rate. Okay, so even if I have a nice recovery of liquid, at the end the overall rate will be less. Okay, because the driving force is also reduced. So high pressures reduce production rates from the reservoir. Okay, so that's something that of course we don't want, and that's why, so just let's wait a moment. And then also when we talk about gas, so high pressure gas occupies less volume and the velocities of gas in the system are less. That means less pressure drop, okay? And that also means higher separation efficiency. Okay, because if you remember, I told you that, or maybe I didn't tell you, but in the gravity separator, you have, when the stream comes in, you have some fluid droplets in the gas, okay, that they have time to go, and that should be, as I told you, the color, and they go, and slowly, it takes some time, some distance to be deposited, okay, in the liquid layer. So if the velocity is very, very high of the gas, then they won't have enough time to deposit because they are going to be traveling quicker. And most of them will be carried out in the exit of the gas. Okay? So usually I try to have low velocities to have higher separation efficiency. But the problem is that, again, I have high pressure, then I'm sacrificing some production. So the conclusion of this discussion is that usually for oil, the pressure of the high pressure separator is 50 bar or less. Okay? And that's just because it's a liquid production and it's very much influenced by the pressure drop between reservoir and separator. If I can take it even lower, that's great. But I have to be careful with the amount of gas that I have. If I go down too much, for example to 30, 20 bar, then the gas will occupy a big space and then my separation efficiencies will be very bad. Okay? Now usually for gas, PHP can be higher. Okay? It can be at least 50 bar, but also can be higher, depending also on if I can recover a significant amount of liquid from that gas. Okay, because I know that if I increase it, then I can convince most of these guys to go inside, and then I can produce more liquid. Okay, and maybe to go, for example, if you see the case of Christine, is 87 bar. So to go from 50 to 87 maybe won't signify too much on the overall production, because I get more condensate. Also another, just a kind of a side comment, another way to convince this guy is to use more stages, more separation stages. Improve liquid recovery. So, but that's usually also a problem, because if I put too many, they start to occupy too much space in the platform, and space costs money. So usually in the North Sea we use 3, it's like the maximum we can have, and we try to live with it, but there are some other places that maybe use 4 or 5 stages just to improve their liquid recovery. It's like you can say that this is, the pressure is kind of convincing this, and the other one is like if you try to convince someone suddenly one day at a time, then they might believe in you and they might change. But if you try to do it, okay, tell me now, where do you want to go? When they are forced to take a decision, they all the time want to go to the gas. Okay, so this is kind of a slow convincing process to have many stages. Okay, then okay, now we have the Okay, so that's so usually the separators in the North Sea, usually separators are three-phase separators. Okay, even though most of the water is separated in the first stage. Okay, and the separator looks something like that. You can have different types, but you have like a weir that separates. So here you have the inlet of the three phases, water deposits at the bottom, and then you have the liquid separated by a weir in between. Okay, so the oil kind of, here you have an emulsion that separates slowly, and then it overflows over the kind of the oil chamber, and then from there it is drained. Okay, and gas. So that's how you achieve this. I think you also have it here in Christine. You have the three streams coming out, and that's why also you have that the water usually goes out from the center, the oil goes on the farther side, and gas always in the top. Okay, because it looks kind of resembles the physical. Also, something noting here, worth noting, you have a bunch of internals that they are just in charge of making that the droplets will heat against them, and then at the end to collect them and take them slowly to the liquid phase. And also, if you see here, you have this vortex that what happens when you're taking a shower, you are, if you have a tub or if you have in the sink, you see the water forms like a torch. Okay, so that's just to break, because if that forms, then that surface can start going down, and you have some oil that is pulled into the water exit. Okay, or the same thing in the gas for the oil, to avoid the formation of this vortex. So okay, really there is really, when we the facilities usually have a maximum capacity of processing capacity, first of gas. Okay, that comes given by the dehydration unit and by the compressors that I have. Okay, usually the compressors, they have a limited power. If you see, the delta P is all the time fixed. Remember, the compressor depends on two things. Okay, the power of the compressor, the delta P that is breaching, and then the amount of rate that is circulating. So if this one, so the delta P usually is fixed, so what changes is the amount of flow that I'm circulating. So the compressor gives me a limit on how much gas I can process, and also the dehydration unit has also a limit. And also then I have the processing capacity of water that depends on basically the cyclones. Okay, and then I have the processing capacity of liquid that basically is given by the level that I have to have in the separator. Separator capacity or separator level. Okay, we're just going to finish, don't worry. Separator level. Okay, so usually those things are the ones that give me more or less the cost. Okay, these three things. So if I want to have, for example, a high capacity of gas, it's like almost go proportional. Okay, that if I want higher gas capacity processing, then I will need a bigger unit, then will be more heavy, and then will cost a higher capex. Okay, and also the same thing with water. So we try to find, using economical analysis, trying to find kind of where is the break point. Okay, where the capex the production increase, but also the capex doesn't increase too much, such that the NPV is maximized. Okay, something similar to what we have done with the number of wells. Yeah. So like one example that I want to put here to conclude the class is the example of hydrogen. Okay, I just was pulling some data for you. Okay, and you see that's water production with time, then oil production starts to decline, and then gas production. And you see here these dashed lines, they are the limits that you have. That's the maximum gas processing capacity. Then you have the maximum water processing capacity and the maximum oil processing capacity. And liquid, okay? So if you see, we can include those, for example, when we calculate our production profile, we can include those like a limit. If I reach at any point that limit, what do I have to do? The only solution is to reduce the rate, to choke, okay? So like, if you see that case, for example, the gas started to go up very early, okay, up, up, up. And you see here after that point, it stayed more or less around the limit. So that is an indication that hydrogen is really, you have a limitation in the gas processing capacity. Okay, and because of that, you have to reduce the rates of oil. Okay? Yeah? So what I'm saying is that you use those limits in your production calculations, and they are really going to tell you when do you have to choke. Because for example, if I knock many other fields, what happens is that this one knocks the water maximum water processing capacity, and then I have to choke. I have no other choice. Okay, I have to reduce all rates to bring again back that line to the limit, because I cannot process more. But in reality, try to find, and I can move those values up and down. Okay, I can move these lines up and down, but they cost money. Okay, due to the capacity. The equipment has to be bigger, maybe the platform has to be bigger, and the capex has to be much bigger. So I have to find a midpoint where that increase gives me more production, is kind of more positive to NPV, but also doesn't increase too much capex. Yeah? Okay. Any question before we close? No question? Okay. See you next week.